Hi. Thank you so much for coming and seeing us. We really appreciate it. reInvent is such an exciting time and an exciting place, and there's a lot of stuff competing for your attention, and we really appreciate you giving us some of the time here. I think you know why you're here. I'm Jeff, my colleague Ruslan, and we're going to talk to you a little bit about how you can fast-track changes, Kubernetes platform rebuilds, wholesale changes to your technology and even your organization with observability. I've been doing this for a long time, since before the web, Gopher, Usenet News, things like that. And I want to let you in on a little secret. I don't care about infrastructure, which is a little ironic because it's right there in my title, and people who work with me are probably saying, aha, that explains a lot. But I want to say you shouldn't either. And it's not because it doesn't matter. It matters a ton, obviously matters a ton, but it's necessary but insufficient. And if you are focused on infrastructure, you're looking at the wrong thing, because you need to care about the system. Infra is a piece, code is a piece, architecture, integrations, networking, the clients, where they are, I mean, all sorts of things. And when you invest in observability, you start to focus on the right part of the system. And from there, you branch out and you can solve the real problems. We're going to walk you through our challenges and how what I just talked about helped us get through some interesting ones. Some of it's going to be technical, some of it's going to be organizational. Hopefully there's going to be a little bit for everybody, no matter who you are. And the important thing is that anybody here can do what we did. It takes some discipline and it takes some direction, but it's not magic. And if you put in the time and you apply these ideas, you can get the same outcomes and see some of the same benefits. So we had a great challenge at Clear. Our business grew, and it grew well, and is still growing, and it outgrew our infrastructure, so we decided to make it better. And I would like for everybody or anybody here who has ever had to scale up a system because the demand got too big, anything from a laptop to a production system, just stand up if you've ever had a scaling challenge, if you'd indulge me. And I bet it's probably most of you. So, no, keep standing. Sorry. So we obviously did too. So I would like you to stay standing if you also did it with minimal downtime when you were doing this scaling thing. Minimal downtime, basically zero downtime fixes to your platform. Okay, stay standing if you did it while you were also introducing a new systems architecture. Okay? Stay standing if you did it while you were doing new hardware, in our case EC2, because we're on AWS. All right, not too many people left. How about if you did it while you were also moving to Kubernetes? Systems, whoa. Wow, okay. I think I want to talk to you. Oh, okay. Well, it's, wow. Well, I probably want to talk to you later about whether you want a job. So how about if you did that while you were also moving to GovCloud, AWS GovCloud? Okay? While you were also reducing the costs and making budgeting, while the entire system was growing. And, well, I don't think there's anybody left, but if you were, in 6 weeks. So that's what we did, and we were just going to walk you through some of the techniques we used to go do it. So you may have heard of Clear, clearme.com. If you traveled here, you probably saw us in airports. We are started out as a travel company, but we're more than just an airport security company. In fact, that's just an application of what we do. We are a biometric identity as a service company, and we want to reduce the friction in everybody's lives by bringing strong identity to real-world situations as people move through the physical world. And we're in airports, and we are in sports stadiums, and we are powering biometric checkout of your car for Hertz, and we are also an API platform, and there are more and more integrations coming. And that's part of the reason that we had this lovely challenge of growth. And I want to tell you a little bit about how we got to where we were. This is about our growth story, and I bet it's going to be similar to some of yours. In 2010, Clear was rebooted, and we were in business with one airport. And our technology was completely local. There was no cloud, there was no anything like that. I mean, the cloud existed, but our technology was totally local technology on actual physical cards. By 2014, we were in 10 airports, and we had shifted that to a cloud-based solution, co-located, data center, traditional, I think. And it worked well, by the way. These were all choices that were smart choices to tune what we needed as a technology company with what we needed as a business. In 2016, we were in 23 locations. It was not just airports, it was sports stadiums as well. And we had made the shift from colo to cloud and containers. We did that a little bit early for some companies, and that was really, really powerful for us. In 2018, we were in 38 locations. We had our first API integration, and we were running larger clusters, horizontal scale. In 2019, we were in more than 60 locations. We had multiple API integrations, and we were running clusters of clusters. And that brought us to where we are and that challenge that I mentioned that we just did. And it was a challenge, and these are great challenges to have. I want to set some context for why observability and what you get out of it matters. First part was setting our credibility. This is giving you something to anchor the why and the strategy here. The tech part is the easy part, except it isn't really in your control. You control how you do the technology, but especially if you're growing, you don't control, or you don't get to directly control how your system is used. The access patterns, the concurrency, the frequency, the distribution, as you grow, that changes, and that changes the way the technology needs to operate, and it changes what you do, and it changes the way you think about things. You don't always control the dependencies, upstream or downstream. Hey, when a kernel patch or an underlying infrastructure patch, the patch microcode issue changes your performance profile, or where your downstream partner gets slower, and that changes the way your customers integrate and experience your platform. And sometimes it's cost, and sometimes it's locations, and basically the rate of growth is something that's out of your control, especially if you are growing, which is an awesome challenge. That's a great problem to have, but it does make it a little bit difficult. And that brings us to the Kubernetes part. That's why we chose Kubernetes. There are all sorts of ways to tackle growth in the technology and the infrastructure, and Kubernetes, we think, is a really solid approach. It gives you a contract between the applications and the infrastructure that is portable and consistent across scale and lets you pivot and iterate on your system at multiple dimensions in a decoupled way and coordinated without having to change everything. So you get vertical and horizontal scale. You can make bigger EC2 instances underneath it. You can make more pods. You can increase the memory size of your containers, your pods themselves, and you can always scale horizontally. And you can do clusters of clusters if you want to, with all the same deployment mechanisms, and that's a very, very powerful thing to have. And you can do that if you want to do it yourself at small scale with open source, perfectly available to you. If you want to go and get a commercial support offering, there are plenty of vendors out there. And there are platform as a service offerings. AWS has EKS and ECS. Those are great. And that gives you, as the technologist or the strategist, or the CIO or CFO, a lot of choices about how you go and you implement your technology strategy. The other part of the challenges of growth is the people and organizational challenge. And that's hard. That's a lot harder. And as a technologist, I'm a tech person. I tend to think of that second, but in a lot of ways, that's the most important one to tackle. You really get two splits here. You get overconfidence. No problem. Hey, I got this. I know exactly how this works. And of course, when the growth is happening, that's not really true. The system and the usage is changing out from underneath you. And when you think you know more than you actually know, you make some obvious mistakes. Hey, you run out of capacity because you thought that you had plenty of space. You You have an alert that triggers at the wrong time because it used to be fine, but now it's not because everything is bigger and faster. You get the, oh, I can take this offline, but you don't realize that, wait a second, now those two parts of the system are coupled, and if you take that offline, you're actually going to go take part of your system offline. And you get subtle ones, the outliers. The, hey, my alert and my monitoring dashboard says everything is fine because my average looks okay or my median looks okay, but what used to be 0.5% of your customers having a slow experience is now 10%, but you don't see it and you're not thinking to look for it. You get the, oh, I can do some maintenance here, I can take this offline, but what used to only affect one person or 10 customers or members now affects 5,000 because the rate of usage is so much higher. And you end up making poor choices because you think you understand the system, and that's really not okay when you're growing. You want to deliver a fantastic experience all the time. The inverse, and in some ways I think worse, is underconfidence. You know that you don't know, and because of that, you don't want to act. Hey, can you go make this change? Nope, sorry, can't do that. And that's as big of a problem. That's a strategic problem as well as an immediate problem. That gives you legacy systems, it gives you unpatched code, it gives you, whatever you do, don't reboot that box. And that's a problem. And it also gives you the subtle thing, which is the killer for an organization, which is fear, malaise, fear, uncertainty, and doubt, risk aversion, a blame culture. It was working, it used to work, it was fine until, well, not him, he's really good, but until, you touched it. Ooh, sorry. And nobody knows how that works, so let's not do anything whatsoever. The safer choice is to do nothing. And that is a cultural problem that is just the killer for organizational growth. And it takes, in a lot of ways, a lot longer to unwind than the technology issues. And tech can be hard enough, even though I said it was easy. And that brings us to observability. If there's a single investment that you can make in your technology strategy, your organizational strategy, your implementation, it's in observability. It's in measuring the right types of things. Because those other two that I was talking about, including the technology one, the three things, really ignorance is the core of those problems and challenges. And if you're looking at the wrong things, that you perpetuate that problem. And investing in observability speaks directly to turning that ignorance into knowledge of the right stuff. And we're going to talk about our playbook for observability as we applied it to go make that very, very fast, multi-dimensional technology change, successfully, I might add, which makes it a lot better, and just show you. And the steps that we did are entirely generalizable. This is, anybody here could do it. You should do it. We believe in it. So, tools. Tools don't do the work. Tools help you do work better, but they do matter. And picking the right ones is helpful and useful. And there are a lot out there. They're commercial, there's open source, and if you apply the techniques with whatever tools you choose, you can go achieve what we achieved. But I will say that we like the tools we've picked. Metrics, observability, SignalFx. Monitoring, SignalFx. We also use logs. We use data that's coming out of Kubernetes. For testing, we chose Locust, a Python open source framework for doing test development. We also used SignalFx as a collector for our test data, and we'll get into that a little bit more shortly. And for the analysis, we used SignalFx. We also used the universal scalability law and a modeling tool called Pretty Darn Quick Modeling, is that right? And we're going to talk to you, Ruslan is going to talk to you about exactly what that was. And that was really helpful. In particular for us, SignalFx was super useful because it got out of the way. We got to just apply it and then start using the data that we could see and not having to spend a lot of time thinking about how to make the tool work, and having the tool guide you towards the right types of views is a very, very subtle but very, very powerful thing. And it allowed us to focus on our business and our challenges and solving our problems instead of solving the tooling. And that's a nice, I wouldn't say it's a luxury, that's a necessity. That's something that you should be thinking about when you pick your tooling. So, playbook, step one. Start collecting the data. Don't overthink. Until you've done this, you don't know what you need to know. very standard thing. You don't know what questions are the right questions, what are the wrong questions, and the opportunity cost is pretty high of delay, so start. For us, the metrics were very easy. SignalFx, again, a very nice tool for that. And we got too many instead of too few. And that's its own problem, but I'll pick that one over not having visibility any day. And tracing, for us, we're beginning our journey there, so that's a thing. We'd love to talk to you about where you might have gone with that. That requires a lot more insight into how your applications work. That's part of the point. But you don't actually need to get to that in order to start deriving benefits. And this standard dashboard about Kubernetes comes right out of the box. Very helpful. Step 2, baseline. And this is not a baseline that's a spend 6 months doing a meta-analysis of your system and doing architecture diagrams and all those things. Those are great things to go do. But this is observations of your system as it's being used by your customers at its interfaces. And that allows you, that is your baseline for how your system behaves. That is the best possible baseline because it's real. It comes from real life. It comes from real data. It comes from real users. There is no hypothetical here. This isn't a model. This is the actual data of your system in real time. The important thing here, or an important thing here, is to measure from the outside. I know for me, as a technologist, systems architect kind of person, it's very tempting to be measuring, CPU utilization, or I/O wait time, or the number of processes, or load. And those are good measurements, but they're measuring the wrong thing. I don't care about infrastructure, remember. So you want to measure how it's being used at the interfaces that your system exposes, because that is the experience that the people who are using your system are going to have, and that tells you what's happening. All those other metrics are really important to tell you why and where you might want to go or what you might want to touch, but those aren't the ones to look at. And you want to focus on the demand, the inputs into the system, because those are the things that change as you grow. And if you are observing those pieces of the system, then you can make sense of almost anything else that goes on, including all of the detailed data that you can get when you've got good tooling. Then the next thing, third thing, build some tests. Again, don't overthink this. You can't solve everything. You don't have to solve everything, in fact. You want to start by looking at the busiest part of your system and build a test around that. You want to build small functions that test that piece. You're not necessarily going to run them in isolation, but you want to build them as granular, isolated pieces, and then you can start to build those up into test scenarios. You want to instrument the test framework. Really, really important that you get the data that your tests from the client side, that you get that data into your observability platform. Database, a spreadsheet, SignalFx, however you're going and doing that, you want to see that data because that's your record of what happened. And again, your underlying metrics are the record of why. You use your metrics and your baselines that you observed before to tune your test. You don't necessarily need to know in advance exactly how to make it work because you can build it up, you can increase the concurrency, you can increase the wait times, and as you tune it, you can see your test results align with your observations of your actual usage, and then you've got something that's pretty close. Again, black box here. Later, you can have good inferences. And then a little thing, you want to keep track of what you did, and ideally you want to keep track of that in with the test results as metadata. In Locust, we were able to very easily use their event handlers to hook in to SignalFx's events and then have a record of what the test was doing, when it was doing it, right there with the data about the concurrency, the latency, things like that. And that really made it a lot easier later, a week later, a day later, somebody else who's looking at the data to say, oh, okay, I get it. This was a test that was 10 users of our enrollment API. Got it, cool. I know what to look for other places. And then run some tests. This is the data from tests that we ran, collected in SignalFx and visualized, and it is showing the latency, the throughput, and you can see some of the ramp times there, basically as load was introduced. We run this by using Jenkins, our orchestration system. We have this automated. Because the tests were built up in a granular way, they're parameterized, and we can basically tune and tweak them dynamically and then have it done automatically through our orchestration system. This is not running on somebody's laptop. It's really important for us, in fact, as an identity company, that we never have our data leave the secure enclave where we keep it. And very tempting, I've done it, not at Clear, at other places, to say, oh great, I'm gonna go do a test, let me get the test data and put it on my laptop because it makes it easy. It's easier. And that's convenient, but if you have your test output, the client output, collected as metrics, same metrics that the observability parts of our system are doing, and you collect it in the same place, then you don't need to have the data on the laptop. And in fact, you can do all sorts of really interesting tests by moving the test close to where your data is. And that ends up being very powerful. If you've ever struggled with, well, how do I test in real life? Because I know if I test on synthetic data, it's going to not be quite right. This lets you bypass all of that. And you can look at the metrics and traces. They're right there. They happen in real time. And if something goes wrong, you look at your logs. Log aggregation, that's the other piece. Very, very powerful pattern. So that probably seemed really simple. Maybe it did. And in some ways, it's because it is. But I want to have my good friend and colleague, Ruslan Rusu, talk to you about what you can do if you've made those basic granular investments to get the tests ready to go and your data collected. You can do some astounding things, at least to me, about predictive analytics, about capacity and performance without having to do exhaustive test runs of testing all the possible permutations. And it gives you, with shockingly little extra work, the ability to start to answer questions like, how much time do I have left? How much capacity is remaining, both technical and organizational and architectural, and it's really cool. So with that, hand it over to Ruslan.
Okay. Thank you, Jeff. Good to see you here. So let's dive in. So usually, if you are in the business of moving fast, then you need to be sure you're not breaking things. And in order to guarantee that, you need to have a set of disciplines in place. And one of the disciplines I'm responsible for is capacity planning and performance analysis. So when you come in this space, what makes this quite challenging is that systems don't scale linearly. They rarely do. And what it makes it even harder for human beings to interpret the headroom and how much capacity you need is our mind is not able to function in a non-linear way. And we'll walk through the journey and explain you why. But given you are in an environment where observability is a first-class citizen, then you can start proactively collecting all the metrics and all the resource utilization so you can take better decisions when the time comes in. So if you have something like SignalFx, it's going to collect side-by-side application metrics and resource utilization, like CPUs and all that stuff. But if you are unlucky, then you can fall back to different techniques. For example, you can put in the logs or instrument your application where you're doing all expensive operation and saying, like, this is the timestamp, this is the name of the operation, and how long did it take. So after you have the system running in production, then you can tail the logs, do some post-aggregation, and get the throughput profile and the latency distribution. So there are a new set of runtimes. For example, in Java, you have Drop Wizard. And this application comes with pre-instrumented metrics on all their resources. So they help in this situation. But once you have this data, it becomes like the left 5% where you can transform the metrics into information to your superiors. And let's dive in to see what does it really mean. I bet everybody has charts like this to monitor their systems. There is one caveat to these charts. You'll see. It has a temporal component. What this temporal component makes, it makes it hard to judge about the capacity. you can understand what the system is doing right now, but it doesn't show you the whole picture. And let's dive in. When you want to understand what's the performance profile of your application, you want to make sure that the system is not operating in an error state. Because guess what? Operating in error state, you can produce a really high throughput at a low latency by throwing out 404s. So make sure you're not doing that. Now, the second one. If you look careful at these charts, they are three. And if you go by acronym RED, where you have response time, errors, and latency distribution, they're very important. So that gives you the signal that the system is operating correctly. And now if you look at the first chart and the second one, you're going to see that there is a very strong correlation. When your system is operating in high throughput, the latency spikes. And that's a very good indication on showing you how your system is pushing back for you under the load. What makes it hard is, for example, you don't know if you added capacity, by how much did it help. It's hard to quantify that part. So we're going to come back to this, but let's move on. So what kind of information is helpful if you want to talk to your superiors in order to articulate the capacity? Well, if you use Little's law, which tells you that multiplying the latency for that particular delta time by the throughput, then you're getting an argument n, which is called the load. Now, if you use that value and plot side by side all the traffic you got through the day on two charts, the first one is the throughput and the second one is the latency, you're going to get a continuous curve where it's showing you how your system is pushing back under the load. And that's very important because in this situation, you can see at which load level how hard the system is pushing back and how it's degrading. Let's look at the first chart, which is the throughput. You can see as you start pushing load in your system, it starts growing linearly. But a little bit in, and it started falling down from linearly. It's supposed to be a curve like this. And that is showing you that there is contention on making the work happen. If you look on the next chart, that is the latency distribution. And you can see that at low n, it tells you that it doesn't take much to get the work to the system. It's just the amount of what does it take to execute the work. As you start pushing in, then you can see the interference is starting kicking in and your latency start increasing. And guess what? When the arrival rate of requests in your system is increasing the throughput of your system, then you will see that the latency is going to go to infinite, which is going to make bad things happen in your system. So given you've seen the part which is not helpful, this is what we need, and how do we get about coming to this point? So it implies the throughput curve is something like this. It implies that you need to pick the level which you are simulating in your experimental environment, where you can get the whole size of the curve. And once you run a benchmark with the load levels, you can pick arbitrarily something which represents 1 load level, 25%, you can do 50, 75, 100, and 125. Why 125? Because you want to see when your system is reached the maximum and is going in retrograde scale. So like pushing it further is going to go only worse. And when you run a test like that, you can collect the metrics from the driver's side, and you can collect the metrics from the application perspective, as my colleague mentioned. So you need to have this information side by side. That's the insights you are getting on how your system is performing. So now, once you got this information, you either collect it from the driver's side or you can pull back from the monitoring system. Then you can start doing interesting things. For example, the results of an experimental load are going to look something like this. So you can see in the first chart, which is the n, which tells you how hard is the load generator working. And you see the load level at 1 at 3, at 5, at 7, at 9. And there are like some pieces in between on the first chart. That's the area where you want to differentiate the load levels and do any cleanups. So now, if you look at the second chart in the same line, that's the throughput. You would observe that like at load level 1, the throughput was 5 requests per second. Once you started pushing harder, you've seen it come to 10. But doesn't matter how hard you continue pushing after that, your system was staying flat. And look what is happening at the response time, as we've seen in the previous chart. It was the lowest utilization level at load 1, it was 200 milliseconds, and after was 300, and it was continuous, like growing until it's going to generate timeouts for the consumers. So this is the throughput. So now you can collect all this information which is in these charts and start doing interesting stuff. But wait. The first thing you need to see if the data you got from your load doesn't make any sense. In the sense, like the shapes you are plotting, the throughput should have this shape and the response the opposite way, as we've seen in the reference chart. Once you have charts like this, then you know the system is not operating in the error state, and the data is capturing all the throughput profile until the max. And you can see how latency kicks in and goes to infinite. So once you validated this part, then you can go even further and scrutinize the numbers you've got. So one of the numbers you want to make sure is you look at the load level 1, the first column, and is load level 1, which gave you the throughput of 4.8. That is very important because you need to normalize all other throughputs based on that, and it should be that it should be less than what is the load if you multiply by that. If you look in this, let me see, in this chart here, this is the normalized throughput, is 1. So as you move further, you're going to see you increased the load threefold, but the capacity was only 1.8, which means your system started pushing back. And it doesn't matter how hard you continued to push, you didn't get much value out of the system. You can do even the opposite way to see if you have multiple clients downstream and they push as hard, how efficient or how much of the work is going through your system. And if the system starts breaking, and you'll see, if the system starts breaking, then it's going to exceed 1. And that's going to tell you that the test is invalid. You need to go to do a lot of explaining and dig to understand why it breaks. So now you've given you vetted the data till here, then you can do interesting things. In 1993, Neil Gunter proposed the universal scalability law. And this is the ingredient which allows you to understand how, like, the opposite, why your system doesn't scale. So this is the information you need to have when you talk to your engineers or when you talk to your salespeople or the people which do the acquisition. Let's dive in. It's the same data we had in the previous chart. And you look at the first two columns. One is the load level and another one is the throughput. So if you do statistical regression over the equation underneath, when the regression is completed, you are going to get two coefficients. One is alpha, another one is beta. Why those coefficients are, it's important that you quantify them. They represent why your system doesn't scale. Alpha represents how much contention is the cause for your system not scale. The second one is the coherency. So let's dive in. So this is the information you can talk to the engineers which designed the system on asking them, hey, is there any way we can use a better concurrency algorithms on this critical path? Or discussing with the people which partition and put the data in the system. Hey, in our system, beta is too high, which tells us there is a lot of crosstalk in our topology, which causes our system ongoing in retrograde scale. There is one more thing I want to mention here. So if you get alpha and beta 0 in this fitting, it's telling you that your system scales linearly. If you get beta is the contention, the cause, and if you get, alpha is the contention, beta, and if you get all of them, is telling you that at some point your system is going to be in retrograde scale. It's going to pick the max and go backwards. Now, if you look, it's very hard to see on this chart, but you can see here the bubbles, those bubbles. Okay, it's hard. The bubbles is the experimental data, and the interrupting line is the data which has been produced with universal scalability law. And if you see the measurements we did, 1, 3, 5, 7, 9. But if you look at the results we have here, and here, is telling you that the Nmax, the max load level your system can sustain is 5.7. We even didn't have to do a measurement to know that. It was easily inferred from the data. So that's one of the keys which you can use to understand how your system, or why your system doesn't scale. You can use to do repeatable experiments when you refactor the system, or you realign, or when you added the new hardware, because it should affect where is the throughput and what's the direction you want to go. So now, once you understand how your system is being composed, you can use that understanding to mark it as a network of queues. And if you understand the runtime characteristics from your load test, then you can augment the queuing network and start trying to see how your system is going to behave at different load level. This is an example how you capture the behavior of a system which has a queue and 2 processors. And illustratively here, I wanted to explain how a system which has 2 processors and 1 queue, given that processing a request takes 0.2 seconds, is going to affect the performance profile under different loads. You can see as the system reaches the utilization of 100%, your response time becomes very high. So this is the information which is very helpful if you want to define SLAs. You know what is the hardware profile, and you know where you are going with. Now, once you can validate at the different load levels we've done through the experiments with your model, if you see that it holds up in the area of 10–15%, you can continue to consider it to be very good and move on and do more interesting things. Now you are in a position to experiment on see what other things you could do with your application without writing any code and doing any expensive work. It's mostly, for example, if we take as a baseline the previous example, then you have the original system has 2 CPUs. And in this topology, you can see the response time at high utilization is going over a second, and the throughput is 10, right? So now the interesting question is, okay, so if I get twice as fast CPUs, what can I get out of my system? Well, on the second column, you can see that the response time dropped from, so the response time dropped from 2 to a half. This is the factor of having faster CPUs. Now, if you look at the residence profile, you can see that now your system can cope better under load and give you a better response time. And that's important. And look at the throughput. Throughput was 10. It doubled to 20. And now you can have this conversation and say, oh, but this is too expensive. Maybe we can double the amount of CPUs. Okay, so what we can do, and this is represented in the third column here. Now, even if you are running more CPUs, you can see the response time on low utilization is still the same, but the curve is having a different shape. If you look at the utilization of 50 here and the utilization of 50 here. So now you can cope with load longer at low response time. Well, that's interesting. So what else is interesting? You can see the throughput is the same in these two situations. But the first one is giving you a better response time. So now, if you're curious to understand, like, what do we get if we do both? Okay, if you do both, then you can see the response time is in a half from what it was basically, and the throughput quadrupled. So if you go through all these steps when quantitatively qualifying scalability, then you have information on your hands. It gives you an edge if you want to understand how much headroom do you have until you need to provision new hardware. Where are the low-hanging fruits on doing optimizations? And this becomes very important if you want to have a culture driven by numbers and not an ego. And all this is possible if you have observability, a first-class citizen. You only have to interpret the numbers and project them in a different way. Thank you, Jeff.
Thank you, Ruslan. I want to reiterate something. If you have observability and you're collecting the data, you can use your test to develop some models of observed stuff. You can do experiments, actual just experiments to go see what happens, but you can also do predictive analytics, and sometimes you can compute those curves that Ruslan is showing up here in advance using your model and give you an idea of where you should go next or what might work or what might not work. And this type of thing is where those infrastructure metrics start to become important again, because you don't necessarily know why until you start looking at what the constraints are. Okay, so I think that's pretty magical, actually. So let's talk about what happened for us. I said a bunch of stuff in the beginning, so I want to talk to you about what actually happened and a little bit about why. The first thing that happened is actually almost so simple, it's beautiful, is that we got observability of the actual system. We ended up with the data that mattered about our application and our infrastructure in a chart that we could aggregate together, and just purely from a day-to-day operation about what's going on, this is just very, very powerful and useful, and having it fragmented gets in the way so much, and having it unified just helps. And we got that, it wasn't for free, but we got that just out of the get-go. But there's more. You know, that's kind of technical operations. This is about the rest of the organization, some of those things I talked about before about ignorance and overconfidence and underconfidence. So we got faster development. The 6 weeks there, when I said all those things we did, part of the reason that we were able to go quickly there was because as we applied the techniques that we talked about, we were getting immediate feedback on implementation and design choices. Hey, should we do asynchronous over Kafka, or do we need to do REST? Okay, well, let's just tweak that and see. Did it matter or not matter, and did it matter in the right way? I mean, looking at the right things. Do we need a cache, or can we read it directly from disk? Should it be a bigger instance? Should it be more of them? Parallel, horizontal scale, vertical scale? Is the limit at the pod? Is the limit in the container? Is it at the network? Is it in the message bus? You get the data right away, and that allows you to bypass a lot of the ego you said before, right? And speculation with real data about your system, super powerful, and development goes faster. A little more subtle, you get a common lexicon of performance across the organization. When you start to have the data that you can visualize the way we showed you before, and people start to expect it that way, they start to think about and talk about, okay, not was the CPU busy, or what was the contention or the latency on a database read, very useful things at times. Talk about what was the latency of that call, right? What was at what concurrency, what was the throughput, what was the error rate, those golden signals, and the organization that starts to talk that way and think that way starts to act in accord with those things, and then you start focusing your efforts on tuning the things that your customers see and experience, and that matters a lot. You get faster testing. That matters quite a bit. I certainly, in my career, have had plenty of experiences where you do a development cycle and then you do a test cycle, and that can take weeks. And if you are embedding people in the teams, that's faster, but you still don't necessarily get real-time information. And that data that we get and that you can get comes in real time, literally as it's happening. And you can also have multiple people seeing it at once. There's not oh, I'm going to take some time to go and codify my results and then hand them over, and you don't lose all that cycle time. And so that's one. And then two, it's calibrated to production in real time. And that matters a lot because, again, opportunity cost is the killer. You get better operations. This matters quite a bit. I'm somebody who's on the infrastructure and operations side of the world more often than not. I love this piece. Because developers were using the observability tools to help guide what they were doing when they were implementing, they spent time instrumenting the right parts of the code and exposing and showing the real constraints of the system. And that means that operations has that data there from day zero, time zero. And that means that alerts are better tuned to the real constraints of the system. And it means that the things that are the performance constraints are probably visible. And it means that folks who have built the system already have an understanding of what's likely to be the limiting factor. And so when there's a problem or an issue or a scaling thing, you can have a much more informed conversation, and you can also see the right data. And that cuts through a lot of the speculation about, well, no, you need faster CPU, or no, actually that's a bad architecture, or you can bypass all of those things that get in the way of growing. You, of course, end up with the right infrastructure too, which helps quite a bit. If you have a V or SV or a C in your title, or you've ever had to answer a question about why does this cost so much, or how much longer will this grow, or how much should we budget, all of the things that we talked about there, you can start to answer those questions in a way that is actionable and probably correct within some margin of error. How will this scale? Is what we're doing efficient? The things that kind of matter when you're talking about a budget or a strategic investment, how much time do we have left before the track that we're on now, given our architecture and our implementation, will basically hit its headroom? Do we have a year? And we can fix this by just adding hardware, scaling up vertically or horizontally, in which case you can spend more time on growing your business, or you can spend more time on adding a new feature. Or do we have 6 weeks? And you know what? Are we in some position that it doesn't really matter, right? There is no adding hardware that's going to matter. We have a model that's going to give us an idea of where we're going to top out. Or you can also say, hey, are we over provisioned, and how much leaner can we get? And you can model that in advance to give you an idea of what's likely, and then you can do an experiment, and you can get data really quickly, and that matters so much for knowing where you're going to spend your capital. And again, time, if you're growing, in particular, a startup or limited market opportunity, time and opportunity cost matters a lot. Last one here. So some takeaways, summarize it all. Hopefully you already have this. With observability, it's the one investment or a single investment that drives many outcomes: technical, operational, planning, budget. Very, very powerful. Very few things in technology get you so much bang for the buck. You can go faster if you know what's actually happening. That allows you the freedom to go and iterate very, very quickly and not lose time to speculation or to just basically branches that are not going to pan out. Having your data in one place, both the input side and the output side and the consequence side, and being able to see it together is the most powerful thing you can have for technology operations and growth. And if you've done those things with just a little bit of extra analysis, you can get capacity and performance analysis, predictive stuff, almost for free, including, this is something that Ruslan mentioned in passing, but I want to bring it out too, you don't necessarily need to do experiments. You can, if you are observing your system in real time, you can pick times of day where you know you've got different concurrency and load, and extract the data from that and use that to build your model and give you an idea just based on the information you already have about what your predictive analytics was going to show you about where you can go. And that's just, yeah, that's why we're here. And that was a really, really powerful insight to have, and it allowed us to go very quickly. So with that, thank you very much. We really appreciate the time, and we'll have Q&A.